Hi, I'd like to discuss with you today why do I think the neutrino mass ordering might be determined quite soon. In the last 25 years or so, we have obtained data from different experiments that are consistent, except for a few anomalies, with the so-called standard oscillation paradigm. In this paradigm, flavor eigenstates nu1, nu-mu, nu-tau are a linear combination of mass eigenstates nu1, nu2, nu3. Solar atmospheric reactor and accelerator experiment, neutrino oscillation experiments, have established that there are two independent mass scales that drive the oscillations. The delta squared 2-1, the so-called splitting in between the solar pair, or the so-called solar scale, is 30 times bigger than the other scale, the atmospheric scale, which tells us that delta squared 3-1 is approximately equal to delta squared 3-2, and they are normally called delta square atmospheric, either one. Okay, because the experiments also have established that there is a hierarchy among the elements of the first row of the neutrino mixing matrix, that is, absolute value of UE1 is bigger than the absolute value of UE2, bigger than the absolute value of UE3, we can use the electron-neutrino fraction to label the mass eigenstates. Nu1 being the state with the most electron-neutrino fraction, Nu3 being the state with the least electron-neutrino fraction. In that manner, we can describe normal ordering of the spectrum as the ordering where the heavy state is the one with the least electron-neutrino content. And in this case, delta m squared 3-1 is larger than delta m squared 3-2, and both are larger than 0. So they are positive. And we refer, because delta m squared 3-1 is the largest scale for normal ordering, as the atmospheric delta m squared in this case. Since in the other case, the spectrum is inverted, that is, the state of with the least electron-neutrino content is the lightest, delta m squared 3-1 and delta m squared 3-2 are negative, and the absolute value of delta m squared 3-2 is bigger than the absolute value of delta m squared 3-1. So in this case, we will refer to as the atmospheric neutrino scale as the absolute value of delta m squared 3-2. About 20 years ago, we have shown that in disappearance experiments where the frequency associated with the solar mass splitting is much smaller than 1, the disappearance probability is driven by to high precision, where all the linear terms on the delta m squared 2-1 frequency are considered, by a effective mass scale that in the case of disappearance, nu-e disappearance is delta m squared EE. The scale is a weighted combination of delta m squared 3-1 and delta m squared 3-2. This is exactly what happens for ReNO and Diabase, the reactor experiments, ReNO and Diabase, because the frequency, solar frequency in their case is about 2%. These experiments are not sensitive to matter effects, so matter effects are not very significant for them. The baseline is about 1 kilometer, and also they have no sensitivity to the ordering. They only measure so they have no sensitivity to the ordering, measuring delta m squared EE with high precision. And this measurement, in fact, can be either converted into an assessment of the delta m squared 3-1, a prediction for delta m squared 3-1 for normal ordering, or a prediction for delta m squared, the absolute value of delta m squared 3-2 for inverted ordering. The difference between those two predictions is a factor that depends on delta m squared 2-1 and cosine to theta 1 is about 1% of the absolute value of delta m squared atmospheric. For the nu-mu disappearance, the effective mass square difference, the effective scale, is delta m squared mu-mu, which is a different combination, a weighted combination of delta m squared 3-1 and 3-2, plus a factor that depends on delta m squared 2-1 and all the mixing phases, all the mixing angles and cosine delta. This is precisely the situation for T2K and NOvA, because T2K and NOvA, in T2K and NOvA, the energies and baseline at play make the frequency, solar frequency, about 5 or 4%. So again, this probability is is very precise. What is neglected here is irrelevant. Matter effects are negligible, and so these disappearance experiments have no sensitivity to the mass ordering. But again, their result can be converted either on a prediction for delta m squared 3.1 for normal ordering, or a prediction for delta m squared 3.2 for inverted ordering. And the difference between those is, again, similar to the one that we had for the nu E disappearance experiment, delta m squared 2.1 times cosine 2 theta 1 2, but we have an extra term that depends on a sine theta 1 3 and cosine delta average between the assessment that we can have for this using normal ordering and inverted ordering. When I derive this expression, I should call your attention that I took sine 2 theta 1 3 and tangent 2 3 to 1. This is what data tells us. So this is quite precise, at least to the level we need. Using these differences by the combine of the difference for the predictions of delta m squared 3.1 normal ordering, an absolute value of delta m squared 3.2 inverted ordering for nu E and nu mu disappearance experiments, we are led to the mass ordering sum rule formula, which must be obeyed in any case, right? If normal ordering is the correct ordering, so we expect that within the experimental uncertainties, delta m squared 3.1 normal ordering for nu mu disappearance experiment must be equal to delta m squared 3.1 normal order for nu E disappearance experiment. On the other hand, if inverted ordering is the correct one, the absolute value of delta m squared 3.2 given by nu E disappearance experiments must be equal to the same for nu mu disappearance experiments. And also, our formula tells you that the difference between the wrong assessments would be approximately a few percent. What we have today is the fact that the assessments for normal order, inverted ordering, the absolute value of delta m squared 3.1 or absolute value of delta m squared 3.2 from combining T2K and NOvA is already extremely precise. The precision is today around 1.2%, which is a value that starts to be interesting. And in fact, what we see in data already now, we already see the effect of what we are talking about in the current data. So here we see the chi-square for the fit for a different combination of experiments, various experiments, as presented in the NuFit site. On the right, we have the fit to normal ordering. On the left, we have the fit to inverted ordering. On the top panel, we have the fit for various experiments. We have on the parabola, the black parabola is for reactor experiments combined. And we see that, in fact, the prediction for the absolute value of delta m squared 3.2 inverted ordering is bigger than delta m squared 3.1 normal ordering, as predicted by our formulas. And also, when we look at the combination of basically T2K and NOvA, what is given here by this blue curve, the log baseline combination, we also see that the assessment for delta m squared 3, 1 normal ordering, the value, absolute value, the central value is bigger than the absolute value for delta m squared 3, 2 inverted ordering, as predicted by our formula. So, and in fact, in the long baseline data here, we also have the appearance data, and that's why there is a slight preference for the blue curves for inverted ordering. However, when they combine reactors and long baseline experiments, what happens is that normal ordering is preferred. And this is exactly the effect, that we have been talking about. Because when you combine measurements that are not the same independently, disappearance measurements that are independently not sensitive to the ordering, but they measure different combinations of delta m squared 3, 1 and 3, 2. When you combine them, you start to get some sensitivity to the ordering. So what's new is the fact that in a few months, maybe a year or so, I don't know, JUNO, this new experiment, reactor experiment in China, that has a baseline of about 50 kilometers, is going to perhaps publish their first data. JUNO, the solar frequency in the case of JUNO is not negligible. In fact, it is very important, it's central to make JUNO able to assess mass ordering by looking at phase shift. In this formula here that is exact, that we presented some years ago for the probability, for the nu E bar probability in vacuum, you can see that there are two things that can be measured here. We can measure the delta m square EE, and we also can measure the sign of the phase, and the sign of this phase is what is going to tell us if it's positive, it's normal ordering, if it's negative, it's inverted ordering. However, we have, this is extremely difficult measurement. There are many systematic effects that have to be taken into account. It might take a few years for JUNO to be able to differ normal ordering fit to their data to the inverted ordering fit to their data. However, a few years ago, we showed that even before JUNO can actually tell normal ordering from inverted ordering from a chi-square significance point of view, they are going to be able to measure the absolute value of delta m square EE very well. And in fact, their data are going to fit to delta m square EE extremely well. One for inverted ordering, one for normal ordering, with great precision, either one, same precision, either one, but they are going to differ by a factor 1.8 times 10 to the minus 5 electron volt squared. Okay, and then this is going to be very important in combination to what we said before, because they claim that in 100 days they are going to be able to improve the precision on the absolute value of delta m square EE from 2.5%, the current precision of the array, to 0.8% in about 100 days. And their final precision, they claim, is 0.2%. With that perspective, we can now assume that T2K and NOvA will not improve their combined determination of delta m squared 3.1 or the absolute value of delta m squared 3.2, which is currently, as I said, at a precision of 1.2%. So the magenta curves, the parabola in the top and bottom plot for normal order, inverted order, are exactly these measurements, assuming that they are not going to change. But now we can speculate what happens if JUNO measures some value, central value, for the normal ordering, which will also correspond to a shifted central value for inverted ordering, with some precision. We're going to vary the precision and combine the chi-square for normal ordering combine the long baseline chi-square with the future JUNO chi-square, and the long baseline inverted ordering chi-square with the future JUNO chi-square for inverted ordering, shifted by the amount that we have determined. Okay, and we are going to do this as a function of the precision of the measurement. So we're going to vary the precision of the measurement, which means that we are going to vary this, how this parabola is going to open or not. Okay, we are going to vary the precision of the measurement. Yeah, we are also going to value the central value they are going to be able to tell us. So we don't know what is going to be their best fit point, right? So we are going to vary this best fit point. And then we are going to compare the chi-square of normal ordering, the minimum chi-square for normal ordering, the minimum chi-square of inverted order of the combination. So this takes us to this fan plot. So on the horizontal line, we have delta m squared 3.1 as measured by JUNO. So JUNO can measure any of those values. On the vertical line, we have the precision of the measurement. And on the right, the blue part of the plot is when delta chi-square minimum is positive, so normal ordering is preferred. In the red part of the plot, inverted ordering is preferred. So we show here the points for diabase measurement with the current precision, assuming normal ordering, and also for the reactor combination of diabase renal as given by Afoot with the associated precision, right? Current precision. So we see that if JUNO is able to measure some value close to the one of the reactor combination, so in about 100 days, if their precision reaches 0.8%, they can tell by their combination with the long baseline experiments together, they'll be able to tell the normal ordering is preferred at about 3 sigma. So this plot is very useful because as soon as we have some measurement by JUNO, we can go direct to this plot and know what is the precision of determination of normal ordering or inverted ordering by a combination of JUNO results with the long baseline mu disappearance experiments. So stay tuned for the first JUNO results. Thank you.